we were looking into testing of DC machines, and we have seen the Swinburne's test. An example also we have seen the extra test class. Today also we look into the example. Okay. So the example was like this. When running on no load, the motor takes when running on no load, the DC shunt motor takes 5 amperes at 400 volts. At 400 volts. The armature resistance is 0.7 ohms. The armature resistance, or we can say the armature resistance is 0.5 ohm at cold state. Is 0.5 ohm at cold state, and field resistance is and field resistance is 220 ohms. Find the output and efficiency of the machine. Find output and efficiency of machine as motor and generator at full load. As motor and generator at full load. Taking a line current at full load, taking a line current 53 amperes. Taking a line current 53 amperes. Find the change in speed from no load to full load. Find the change in speed from no load to full load. So this is nothing but speed regulation. Okay. This is speed regulation. We calculated voltage regulation in transformers and alternators last time, which was change in voltage from no load to full load. So this is speed regulation because I am finding the change in speed from no load to full load of the machine given. So what are the given things? The no load line current I naught is 5 amperes at voltage 400 volts. The armature resistance is 0.5 at cold state. So I have Ra cold is equals to 0.5 ohms. Okay, and field resistance RSH is 220 ohms. RSH is 220 ohms. Find output and efficiency of the machine as a motor at full load taking a line current of 53 amperes. So my I is or IL is 53 amps for both motor and generator. So find the change in, uh, so what I have to find here is I have to find efficiency of motor. Obviously it is at full load, so I don't mention it. Efficiency of generator and uh, speed regulation. So these three things I have to find out. Okay. So at the very first, I should be finding what is the hot resistance. Solution. Because in the previous example, it was not mentioned that whether the resistance given zero point 0.9 ohms was a hot resistance or cold resistance. In such cases, it is by default we have to assume that as hot resistance only. When it is not exclusively mentioned that whether the given resistance is hot or cold value, we have to consider that as hot resistance only. But here it is mentioned that the given value 0.5 ohms of Ra is cold resistance. So therefore now I have to transfer it to hot resistance. Therefore, hot resistance of armature Ra is equals to 1.2 multiplied by Ra cold. This factor we have seen in the theory. Okay. So it is equals to 1.2 into 0.5. So I will get it as 0.6 ohms. Okay. So Ra is, I do not mention Ra as Ra hot because already we have considered Ra as hot resistance only. So therefore my Ra is equals to 0.6 ohms. Okay. Next point is to find out constant losses. Find out constant losses. Okay. So constant losses WC is equal to, first write the expression for constant loss, that is V into I naught no load input minus no load copper losses, IA naught square Ra. What is IA naught? It is I naught minus ISH. What is ISH? It is V divided by RSH. So this is 400 divided by 220 equals to how much?
1.81.
1.818 or 1.82 I will take approximately amperes. Okay. So my I naught is equals to no load armature current is equals to the I naught is 5 amperes minus 1.82 is 3.181818 amperes. Therefore, constant losses WC is equals to V into I naught 400 into 5 minus 3.18 square into 0.6. So WC is equals to it is 1993.9 or you can check 1994 1994. Is it right?
Yes, sir.
Okay, so these are my constant losses. So I will mention constant, sorry, I will take constant losses here. WC is 1994. Next. Now I have to find efficiency as motor and generator. Efficiency as motor. Always draw the circuit diagram. Okay. Always draw the circuit diagram. Don't show the solution without circuit diagram in any of the numerical. So this is V 400 volts. So this is IL or I is equals to 53 amperes. My ISH is 1 point. What we got here? 82. So this is my I. Therefore, IA is equals to I minus ISH. This is a motor. So this is 53 minus 1.82. So therefore, IA is equals to 51.18 amperes. Okay. Now, motor input is equals to V into I. All calculations are at full load only. So we are not mentioning exclusively here. Okay. We are not mentioning separately at full load or not. So motor input, or you can write efficiency as motor at full load. So it will cater all the requirements. So whatever the calculations we are doing, those are all full load values only. So it is 400 into 53 equals to
21,200.
Yes.
21,200.
Yeah. 21,200 watts. Okay. Then motor copper losses. Copper losses in armature. Because other things it is not mentioned. What is the resistance in interpole winding and all those things. Okay. So we'll take copper losses in armature. Or generally you can take copper losses in motor. That will also do. So this is IA square RA. So IA is 51.18 square into RA is 0.6.
One thousand five hundred and 21.63.
1571.63 watts. Okay, now total losses in motor. Total losses WM is equals to IA square RA plus constant losses WC. Okay, so this is equals to 1571.63 plus 1994. So 3565.6. This is WM 3565.6 watts. So these are the total losses in the motor. Now, efficiency eta is equals to motor output divided by motor input. Okay, into 100. So I know motor input, I should get motor output. So motor output is P out is equals to motor input minus losses. You can take this motor input as P in is equals to P in minus motor losses. So this is equals to P in is 21,200 minus 3565.3. So P out is equals to 17,634.36. Is it right?
Yes, sir.
Watts. Now therefore efficiency of motor is equals to 17,634.36 divided by 21,200 into 100. This is percentage efficiency. So efficiency of motor is equals to 83.18%. Right?
Yes, sir.
Efficiency of motor is equal to 83.18%. So one general mistake what students do here during the calculation of any motor problem is they directly try to put the values into the equations through calculators and try to keep the answers directly, which is hazardous. Okay, though it appears little bit lengthy, always try to write the formula or expression, then substitute, then keep the answer. If you do this, the amount of error or tendency of doing mistake is very less. If you keep everything in calculator and keep only the answer, one thing, you will not get full marks even if the answers are correct. Second, the possibility of going wrong with the answers is more. That is where most of the students will lose the marks in the solution. You will be knowing how to solve, you will be knowing what equations to be used, but when you are substituting, you will make the mistake. So because of such silly mistakes, don't lose the marks in the exam. Okay, this is what we observe every time. General in substitution, wherever there is substitution, automatically or generously students will become lazy in substituting by writing the formula. Okay, so when you write the formulas, at least the evaluator will get to know that you know the things. It doesn't mean that only by writing formula like in PUC you'll get the marks. That is not the way. You have to show the attempt to solve. Okay, so keep these things in mind. And these small suggestions will be useful only when you listen to the lectures carefully. Okay. If you are attentive to the lectures, so many such hints will be given to solve in a better way in the examinations. Next, efficiency as generator at full load. Efficiency as generator at full load. Okay. So the same machine now acting as generator with the same line current and terminal voltage. So this is 400 volts. This is 53 amps. This is 1.82 amps. Okay. This is IA. Now here IA is equals to I plus ISH. This is the change. Okay. So 53 plus 1.82. So IA is equals to 54.82 amperes. Okay. Then generator output, we know the output here. So generator output P out is equals to same 21,200 you will get. 400 is the terminal voltage into 53 is the line current. Okay. Then copper losses, armature copper loss is IA square RA equals to IA is now 54 point how much it is 882 square into 0.6 equals to it is 1803.13 0.14 watts. 139 something will get 0.14 watts. Then constant losses WC is 1994 watts. Okay. Next, total losses, total generator loss WG is equals to IA square RA plus WC, constant loss. So this is 1803.14 plus 1994 equals to 3797.13, right?
Yes, sir.
Watts. Okay. Now, generator input, because I know generator output now. So generator input is equals to PN is equals to it is losses plus output, P out plus generator losses. So 21,200 plus 3797.13. So Pin is equals to 24,997.13 watts. Therefore, efficiency of generator is equals to P out by P in into 100. So this implies efficiency of generator is equals to 21,200 divided by 24,997.13 into 100. Is 84.8%. Okay. So this is about calculating the efficiency of motor and generator. Yeah, there is sufficient strength. I will continue with what I wanted to share with you. The remaining part of the solution, speed regulation, we will solve in the next class. Okay. So this solution, I will stop it here because I want to share something. I thought first I will finish that part and then I will take the solution of